Hi everybody, my name is Pascal Urian from Telecom Paris, and I would like to present this poster. The title of the poster is Crypto Terminals, a new open device for securing blockchain wallets. This poster introduces the crypto terminals, a new open devices for securing blockchain wallets. A crypto terminals performs cryptographic signatures and computes Ethereum transactions. This device includes a processor, a touchscreen, a removable smart card, and a Bluetooth low-energy module. Smart card is the core security. It manages cryptographic procedures and associated keys. The terminal is bare metals. It means its firmware, and the Bluetooth low-energy firmware can be erased and downloaded at any time. The software integrity of the programmer that performs this operation is checked by an innovative integrity probe. And finally, a use case is illustrated with a smartphone. Blockchain, such as Bitcoin or Ethereum, rely on distributed ledgers storing transactions signed by users' private key. Secure generation, storage, and use of private keys are critical issues. Hardware wallets aim at preventing keys hijacking by malwares. They are divided in hot wallets, which mean connected to internet, and cold wallets, which mean without TCP/IP resources. Hot wallets comprise smartphone board, website, optionally managing hardware secure module, mobile with trusted execution environment, and laptop. Cold wallet usually comprise devices based on microcontroller units, including secure elements or crypto memory. Some of them are using tablets with trusted executed environment or dedicated crypto chips. The crypto terminals is a kind of cold wallet. They are three security targets for crypto terminal. First is enforcing software integrity. That's to say, preventing malware injection through untrusted supply chain. Second target is avoiding side channel attack. Cryptographic keys can be recovered thanks to simple power analysis. And last, enhancing trust for blockchain transaction. Here are a few examples of attacks against cold wallets. A malware was injected in a duplicate piece of code between bootloaders and firmware, a kind of memory copy attack, which defeated the onboard integrity test. Another malware injection was performed on the same device based on code compression and storage in static RAM. A simple power analysis attack was performed against a cold wallet without secure element, which was using the double and add algorithm in order to compute elliptic curve public key. In 2010, elliptic curve private key were extracted from PS3 console by exploiting the lack of random generators. A private key can be recovered from two signatures using the same random integer. Let's take a look at the crypto terminals features and architectures. The crypto terminals is fully open, both for hardware and software. The removable smart card is the core security. The Java card firmware enforces private key storage, computes ICDAC signatures, and BIP32 key trees. Bare metal terminals. Bare metal approach prevents supply chain attacks. In order to avoid firmware hijacking, all processor memories from the ATmega 2560 can be fully erased and flashed, thanks to serial programming interface ports. The crypto terminal firmware includes a loader module for the CC2541 Bluetooth low-energy modules. Trusted SPI programmer, the 2 KB bootloader is checked by an integrity probe based on the DMAC algorithm. The SPI programmer firmware is thereafter downloading from a trusted bootloader. Let's talk about Big Bang, how to trust the ISP programmer. The ISP programmer is made with a microcontroller's unit at Amiga 8 and therefore runs firmware. The ISP programmer bootloader is downloaded in a trusted place. The device travels through an untrusted supply chain. An application, named Integrity Probes, is downloaded thanks to the bootloader. The integrity probes check the bootloader integrity. The flasher application, the USB ISP firmware, is afterwards downloaded in the programming device. It should be noticed that USB programmers may program each other. The integrity probe is based on the Bijective DMAC algorithm. All memories are hashed in a pseudo-random order according to a P permutation. This calculation generates an integrity code IC. The IC computing time, ICT, is included in the final calculation. All unused memory, flash, static RAM, EEPROM are filled up with pseudo-random values. The integrity probes work with the KeyCAC 256 hash function. There are about 2 power 54 permutation keys. The ICT precision is 64 cycles with 12 MHz clock. The ICT average time is 18,000 with maximum minimum range of 60 milliseconds, about 10 bits of entropy. The computed IC code is displayed as 6-bit integers by blinking LEDs. Here is an illustration of the crypto terminal at work. A serial Bluetooth communication, RFCOM, is open between the crypto terminals and a mobile phone running a hot wallet. This wallet sends the user a command. This command triggers PIN entering by the user. Upon success, this operation unlocks the smart card. Afterwards, the mobiles collect ETHEREUM address bound to the cryptographic key. The hot wallet collects information for this ETHEREUM address from a blockchain node. The hot wallet requests, via the setTrans command, the generation and signatures of a transaction. The transaction is approved by the user. The crypto terminal signs the transaction. The transaction content is returned to the mobile. The transaction is forwarded by the hot wallet to a blockchain node. Thank you for your attention.